Okay, hello to everyone. The subject of this lecture will be differential forms. Okay, so as we're going to see, this is kind of a central notion, another central notion in differential geometry. In order to motivate it somehow, let's consider the following basic question. So, well, we discussed the notion of derivative of a function on a manifold. Let's think whether we can do, so we have differential calculus. Let's think whether we can do integral calculus, so whether we can integrate functions. So let's take, so can we integrate functions on a manifold? So what does it mean? So given a function f on smooth, say, function on M, we want to make sense of integral. So, well, what are the basic properties that we want to have? First of all, one basic property is that this notion must be preserved under diffeomorphism. So if I have a manifold M and another manifold N and a diffeomorphism, let's call it capital F. Then, and let's say I have a function f on N, then it gives rise to a function on M, so namely I can consider the composition. And I have a function f on N. So I can compare these two integrals. And I claim that, well, sort of a basic property that we want is that these two integrals must be the same, right? Because at the end, diffeomorphism is just a way of renaming elements of points of M and N, right? So think of just here you basically have the same manifold and simply give different names to points of this manifold, and these two functions correspond one to the other, right? So this is something that we must have, right? On the other hand, our experience with calculus. So let's think what it means in the case of just one-dimensional manifold. So imagine that you have a interval a comma b. This is my M, and my N is going to be C comma D, and you have a map diffeomorphism. So diffeomorphism from this interval to this interval. So you have a function f, and then, well, we know that that integral, in this case, we already know what the integral is, right? We can integrate functions on an interval. So we have a well-defined, so we can integrate f of x to dx from a to say from C to D, right? But we do know that this is not equal to integral from A to B, integral over M of f of let's say y. I use coordinate y, and here I use coordinate x, dy, right? This is not the case. Instead, what we have is that this integral is equal to integral from A to B of f of y, and then we simply take f prime of y dy, right? This is true, provided that, well, this map sort of preserves orientation, which means that f of A is equal to C and f of B is equal to D. So if you have a diffeomorphism from an interval to itself, well, or maybe let me put it this way, since it's need not be defined, let me rewrite it slightly. I will say that derivative is always greater than 0. So what is the reason for putting this condition? Well, so if you have a diffeomorphism, then in particular its derivative must be invertible, so it must be either always greater than 0 or always less than 0, right? For all x. So as you know from calculus, if the derivative is less than 0, then you should put minus sign here for this formula to hold. Okay, so we will talk later about this nuisance. So in any case, if you have any diffeomorphism, then this is true up to plus minus up to sign, right? And if you want plus sign, then you should put add this condition. Okay. So the kind of the outcome, the conclusion is that even in one-dimensional case, you can't really integrate functions because this formula does not hold. What you can, however, integrate is some quantities which, if you choose a coordinate x, can be identified with functions, but if you choose another coordinate, they are transformed by this complicated rule, right? This is sort of x is equal to fy, so I can think of x and y as coordinates on my manifold, and this f is the change of coordinate function. So the quantities I can integrate is of the following type. So they are defined whenever I have local coordinate, and if you choose a local coordinate, that you can identify it with function, and if you choose another coordinate, then a new coordinate should be kind of this function should be transformed. Well, this quantity should be transformed by this. This somehow leads to the idea of differential forms, and now I want to kind of give you a coordinate-free definition of it, right? So again, the motivating question is the following: what can we integrate over a manifold, right? Very good. So, well, I will give you first an informal definition. Definition of well, formal definition So a differential form of order or degree m is the following: is a map that assigns to every point on my manifold a map, let's say a differential form. I will give a name to this form. Let's call it eta. Okay, so it assigns, this eta assigns to every point m a vector, which I will denote eta of p, which is a vector in the cotangent space. So I take my manifold M, I have the tangent space to M at point P, and I have the cotangent space, right? So here Tp star of M is just the dual vector space, right? It has the same dimension. So I take this vector space and I take its exterior power. M exterior power. So, okay, so this is another finite dimensional vector space. And I want a function sort of which assigns to every p a vector in this vector space. Notice that it's not a function on M with values in a given vector space. This vector space really depends on P, right? We'll later interpret it as a section of a vector bundle, but for now, well, it's clear what it means. So, so satisfying, I don't want to consider arbitrary functions, right? We are doing differential calculus, so I want to consider smooth functions. Satisfying, find a smoothness condition. Very good. So, okay. What this, I say that this is an informal definition because I have to specify what I mean by smoothness condition. And in order to do this, first I want to give you a definition, an example of a form, right? So, okay. So suppose I have a function f, a smooth function. Then I will define for you a one form, so differential form of degree 1, and its value at point P, well, will be just the derivative of f. Well, there are many ways to do, okay, so I will, so my f, I can think of f as a map from M to real numbers. And so this is f. And so its derivative at P maps the tangent space to M to the tangent space at point f of P to R, which I can identify with R itself, right? So that's so I have this map. So it defines for me a linear functional. That's a linear map. That's the derivative of f. So I have this guy here, and I will simply put df of p to be this. So this is an element. That's a linear functional. So that's an element by definition. This is an element of the cotangent space. So for every p, I define a vector. So this gives me a function. And so this will be an example of smooth one form. Smooth one form. Well, again, strictly speaking, I haven't defined for you what a smoothness is, right? So this is kind of a motivating example. That's a very nice differential form. It's constructed from a smooth function. So I definitely want this to be smooth one form. But with help of these forms, I can now give you a precise definition. Okay, so maybe let's first define what it means. So this is a formal definition. A smooth one form on M is a map eta that assigns to every point a vector, a cotangent vector, so a linear functional on the tangent space, such that now I will spell what it means for this map to be smooth. For any chart so what it means is that so I have M, I have U, and a diffeomorphism, let's call it phi, between an open subset of M and an open subset of Rn, right? The following is true. So look, so I have maps from Rn to R. So these are projections. And so this its composition with phi gives me local coordinates xi on my U. So I identify U with an open subset of Rn, so I have local coordinates. In particular, since I have U and I have a collection of functions, I have this one forms, right? So for every point P, I have cotangent vectors that I already defined. So this forms. And so for every point P, dxi of P form a basis for the cotangent space, right? Very good. So now, since they form a basis, I can write every cotangent factor as a linear combination of these basis factors. So I will take my eta. Yes, it's a function defined on all, it's a map defined on all M, but I can restrict it to U. And then on U, I can write it as a linear combination of the following guys. I will put Fi dxi. So Fi is a Fi is a function defined on U. So in principle, whenever I have any map like this, any map eta, its restriction to U can be just formally written as a combination of dxi with coefficients whose coefficients are some functions on U. If you don't impose any conditions on eta, this will be just arbitrary function. Any map like this can be uniquely written in this way. Now, my smoothness condition is that all these functions are smooth. This is a very natural thing to do, right? So that's how I define notion of smoothness. So this is kind of a geometric definition, and the smoothness condition, you see, I define this kind of, I don't choose a differential form is a map like this, satisfying certain property. This property is formulated in terms of local coordinates, but the map itself, well, it's definitely it's just defined using the notion of tangent space. Mm-hmm. So that's this is definition. Well, of course, it would be a pain to check that a map eta like this is smooth, because you have to verify something for all charts, right? But fortunately, it suffices to do it for an atlas. So here is an observation, remark. Suppose I have the following picture. Suppose I have two charts. So I have U. I have diffeomorphism with Rn. And I have another chart. So defined on the same U, this is diffeomorphism to some double, with some W prime in R. Okay. Then, so this gives me coordinates, two system of local coordinates, say xi and yi, and so I can write yi to be h I of x1, xn. So I can express one coordinates in terms of the other. This is this map H, right? These are the coordinates of the map. And then, so you can easily verify that dyi, right, the derivative of function yi, can be expressed in terms of, so this one form can be expressed in terms of dxj as follows. So this is sum of partial derivatives. Well, you take dh I and differentiated with respect to xj, right? So if these two maps are smooth, then this is a smooth function. Smooth function. Well, it's a smooth function. So in particular, you see that so dyi can be expressed in terms of dxj, well, as a combination of dxj, and coefficients are smooth functions. As a corollary, we see that for one form on M, it is enough to verify smoothness for an x. Okay. Good. So now I defined for you notion of one form, and now it should be clear how you generalize it. So definition now an M form eta is a map that assigns to every point a vector eta of p in the mth exterior power of the cotangent space, such that for a system, such that for a local chart, for a system of local coordinates, as above. Eta can be written as follows. Well, eta restricted to some u. It's going to be sum over. Well, so let's go back here. So here I use the fact that dxi form a basis in this cotangent space. Now, instead of cotangent space, I want to consider its exterior power, right? Having a vector space with a basis, we have a basis in its exterior power, right? So the basis in the exterior power formed by vectors dxi1, which dxim, where this I1 IM run through all ordered sequences. So these vectors, for every point P, these vectors form a basis in the exterior power of the cotangent space. So every element of this vector space can be written as a combination of this, right? So every point P, this is a combination with real coefficients. So if you let P vary, you get functions, right? And my condition is that this I1, all these coefficients are smooth. Okay? So that's the generalization. Great. Before I give you some examples, let's introduce some notation. So I will denote by omega m the space of all, well, smooth differential forms. Forms of degree m. Well, so if m is 0, the zero exterior power is declared to be R. So this is by definition will be just functions. So notice that omega m is 0 when m is greater than dimension of m, because then the exterior power of an n-dimensional vector space is equal to 0 in degrees greater than. So very good. So I'll give you two examples. Example one, well, the most basic, the simplest example will be take just for m r, right? Then I have zero forms, which are just functions, and I have one forms, well, and I have global coordinate x. So this is for every point P, this forms a basis in the cotangent space. It's one-dimensional. And therefore, any form can be written as f of x times dx, where f is a smooth function. So one forms can be identified with functions. So let's consider another example. Let's take for m S1. Okay. So okay. So I will give you an example. First, I will give you an example of one form. So let's consider. So I think of circle sitting inside R2, and identify it with complex numbers whose absolute value is equal to 1. And I have a function, the argument, the angle, right? This angle. So argument theta. It's a function on S1. It assigns to every point on the circle this angle, but, well, the problem with this function is that it's either not continuous if you, say, measure angle from, if you said that the domain of this function be interval from 0 to 2 pi, right? Because then it's not going to be continuous here. Or another possibility is to consider theta as a multivariate function. So it's the angle is defined up to integer multiple of 2 pi. And that's what I want to do. I want to consider the argument, this angle on the circle, as a function, continuous function in S1, but it takes values not in R, but rather in the quotient of this group modulo 2 pi z, right? So it's a multivariate function. And so I want to define differential form, which I will call d theta. Well, theta, so a basic example of one form is derivative or differential of a function, right? Theta is not a function, so this notation is reserved for differential of a function. So in order to emphasize that theta is not a function, but rather a multivalued function, I put quotation marks here. And so how to define it? Well, so in order to define a form, you can cover your manifold by open subsets, define maybe by open charts, define one form on open charts, and then show that they agree on the intersection, right? So that it gives you a global form. So that's what I want to do here. So locally, if U is any, sorry, this is this one. If I pick any open subset in S1, which is not S1, right? So it's proper open subset. Then on U, theta has a single value branch, has a smooth branch, theta, from U to R. Right? So, for example, if I remove just this point, then I can consider the argument that takes values from on the interval from negative pi to positive pi. So then this function is going to be continuous. So I have a single valued branch. And I define d theta question mark restricted to U to be just differential of this single valued branch, right? So again, in order to define global one form, I first define it locally for any open subset, which is not everything. And in order to do this, I choose any single valued, smooth single valued branch. I get this function theta tilde, and I can take its differential. This is a one form. It's a smooth one form. Of course, you need to verify that this is correct. So what you need to verify is that d of theta, if you choose another branch, well, suppose you have two branches, right, on U. Let's say that U is connected, say. Then any two smooth branches differ by a constant function. In general, it's going to be a locally constant function. So if U is connected, it's just constant. So moreover, this constant function takes values in 2 pi z. So another branch on a connected U, if you choose branch theta tilde, then any other branch has on connected U has this form. And correctness of the definition means that d of this sum is equal to d of theta tilde. Which is clear because d of a constant function, right, differential of a constant function is 0, or even a locally constant function. So this implies that d theta is well defined.
I'm sorry. What
Yeah.
does it mean to define another branch?
Well, so what I mean by a branch, right? I have my theta, which is a map from S1, or maybe I'd say from U to R mod 2 pi z. What do I mean by a branch? I mean any continuous, well, smooth map. It's not going to be automatically. Well, if continuous is enough, it will be automatically smooth. Any map from U to R, right? That makes this diagram commutative. So this is my argument map. This is theta, and this is my theta tilde. So on U, I want to specify how I choose the angle, right? The angle is defined up to a multiple of 2 pi, right? So for any, it's an element, it's a point here. And there are many ways to choose a lift, right? But for a connected U, which is not everything, a lift exists and it's unique up to a constant function, right? Why it's unique up to a constant function? Because if you have two maps like this, right, another branch, right, if you choose another theta tilde, then the difference is going to be a map whose composition with this projection is 0. It means that the difference between theta tilde and another lift is going to be a continuous function in U that takes only values which are multiples, integer multiples of 2 pi. This implies that my difference is a constant function, right? The difference of these two maps is a constant function. Moreover, it's a function of this form. So this is sort of, let's call it theta double tilde. So I have these two maps.
Okay.
Right? So that's what I mean by another branch. Okay? So great. So this is how the differences, how one form is defined. So notice that it's locally, this d theta in question marks can be written as a derivative differential of a function, namely of this function. But you cannot write it globally as differential of a function. We will give a rigorous proof later. That's an important observation. So, and now any form, any one form on S1 can be written as a function times this d theta, where f is a smooth function on S1. Why is that? Because d theta for every point p, d theta forms a basis. Well, it's non-zero, so it's forms a basis in one-dimensional cotangent space. So that means that any other cotangent vector can be written as a multiple of this. And if you let your point vary, you get a function times d theta question marks. Okay? Very good. So now let's go, what will be the next step? So what can you do with differential forms? So operations.
I'm sorry. And
Yeah.
why, if we have defined a differential one form on every open chart, when can we define it globally?
Okay.
What condition
So,
we need?
so suppose you have, uh, M, and it is covered by two open sets, U and W. Suppose you have eta U, which is a smooth form on U, and eta W, which is a smooth form on W. Suppose that you know that the restriction to the intersection the restrictions are equal. So what do I mean by restriction? A form is a map that assigns to every point a cotangent vector. So in particular, I can restrict a form to an open subset. So suppose that these two restrictions are equal. Then there exists a unique form eta on M, with eta restricted to U is eta U, and eta restricted to W is eta W. Okay?
Yes.
Good. So operations with forms. So the most important operation with forms is pullback. Pullback. Okay. So pullback is the following. So you have, suppose you have a map, a smooth map. So this is, say, M. You have a smooth map to M. So then the pullback is a map of vector spaces from M forms on N to M forms on M. Right? So the existence of this pullback is what makes differential forms a better behaved object compared to, say, vector fields. There is, if you just have arbitrary map, smooth map between smooth manifolds, there is no way, starting with a vector field on M, produce a vector field on M, or vice versa, starting with a vector field on N, produce a vector field on M. So that's because, but you can do this for functions, right? If you have a function on N, then you can compose it with F and get a function on N. And this operation generalizes the composition with the pullback operation with functions, simply composition with F. So how you define it? And let's see why it works for differential forms. It doesn't work for vector fields. So if you have any point P, say on M, we can look at the tangent space to point P, and we have the differential, the derivative map, dpf, from this tangent space to this tangent space. Okay? So, and therefore, we have the adjoint map on the space of functionals. So dpf, I put prime here. This is a map from the f of p star n to dp star m, right? That's just the adjoint map of the dual vector spaces. And well, then by sort of functoriality, I also get a map from the nth exterior power. And I will give a name to this. We'll give a name. So it is, so the tangent spaces map in these directions from tangent space to m to tangent space to n, and the cotangent spaces map it sort of in a different direction. And that's why it's possible to define the pullback. So I will define, so if I have eta, this is a 1 for m form on n. So let's define its pullback. So pullback of n. So pullback, well, that's going to be a form on m. So to every point of m, I want to associate, to every point p on m, I want to associate an element in this vector space. Okay, so let's see what we can do. So first of all, we can take eta and evaluate it at point f of p. This is an element here in this vector space. And then I can apply this differential or joint map, the f prime to this vector, right? That's a vector here, and I apply this map and I get a vector here. So, and you see what goes wrong if you say, if you want to use something like this for say vector fields. If you, well, so the direction of this arrow suggests that you can kind of maybe starting with a vector field on m, you could produce a vector field on n, but then so how you define the tangent vector corresponding to a point of n? You should kind of take the f inverse of this point, but f inverse need not be defined, right? F is not assumed to be a bijection or diffeomorphism. So there could be many preimages. So that's why for vector fields you can do this, but for differential form it works. Okay. So that's a construction, and let me give you some examples, or maybe before. Yes, so that's before I give you some examples. Let's discuss some other operations. So what can we do with differential forms? So well, if you consider just all forms on a manifold M, well, this is a vector space. You can multiply, you can add differential forms, right? Because the cotangent space, as well as its exterior power, is a vector space. You can just pointwise add functions from M with values in the cotangent space. So this is a vector space, but it has even more structure. You can multiply a differential form by a function. Yes? So, namely, again, a differential form is a map from that assigns to every point P of M a cotangent vector. If you have a function, it assigns to every point P of M a number, so you can multiply a form by this number, and this number depends on P, so you get a new form, right? So algebraically, it means that this is a module in the sense of algebra, abstract algebra, module over functions. Well, what it means is that you can add forms, but you can also multiply. So this is a ring. You can multiply forms by functions. So, but there is also additional operation. You can take the
I'm sorry.
product.
You assume that sections of this vector bundle is a module, and not,
Well,
not
that's,
some
I didn't use this. I haven't yet used this terminology. So for me, a one form or M form is a map that assigns to every point P an element here. So if you have a function, I want to think of this as a map that assigns to every point P just a number. So then I can multiply one map by a function, right? Just turn point-wise. For every P I multiply. So this notation,
point, yes.
So omega M of manifold M is the space of all forms. So if you think in terms of vector bundles, you probably see that this is the set of the space of all smooth sections of the vector bundle. But again, I plan to review, explain this interpretation in terms of vector bundles later. So for now, well, I am going to use this definition of forms, and then it's clear how you can multiply a form by a function. So if you locally, you can write any form in this way, where f is an arbitrary function. So if you want to multiply an expression like this by a function, you multiply each coefficient by a function. So, but now it has more structure. It has a structure. You can also take the exterior product of differential forms. So, so namely, there is a recall that we have, if we consider all exterior powers of a vector space, this is by definition direct sum over all M of nth exterior power of the space. So this guy form an algebra. Right? So it's you can think of this as a quotient of the tensor algebra, right? We discussed it at the end of the last lecture. So you have a map from nth exterior power tensor with say M prime T star P M to M plus M prime T star P M. Well, so if you have an element here, it can be written as a combination of can be written as a combination of vectors, decomposable vectors, like this. And if you want to multiply it by W1, that's Wm prime, so the result is going to be just the product V1, that's Vm, that's Wm prime, right? So this defines an associative product on this vector space. It's the non-commutative. If you change the order, you get the product in the other direction is going to be differs from the product in this direction by a sign. The sign is -1 to the power, which is the product of these two numbers. Okay. So now again, a differential form is a map that assigns to every point P a vector here. So if I have two forms, so if one is a vector here, and I have another form, say of degree m prime, I can apply this operation pointwise, right, for every point P, and get a form of degree m plus m prime, right? So это one tensor eta 2 goes to a form which I will denote by eta 1 wedge eta 2, and it has a property that eta 1 wedge eta 2 evaluated at point P is this product, eta 1 of P wedge eta 2 of P, right? So that's what I mean by applying this construction pointwise. So this is not just a vector space. If you consider differential forms of all degrees, it's form in algebra, and it's a module over functions. In fact, well, so functions are zero forms. So multiplication by a function can be interpreted as a special case of this operation when m is zero. So a basic property of this operation is that omega 1 wedge omega 2 is equal to omega 2 wedge omega 1 up to a sign, and this sign is equal to m1 m2, where eta I is a form of degree mi. Right? And this formula follows from linear algebra, from the fact that this map satisfies this symmetricity condition. Okay? So, very good. So, now, so we have two basic operations on the forms. One operation is the pullback, and another operation is the exterior product. And here is basic properties. So, well, first of all, if you have M, say N, this is a map F, and we are given another manifold W, and let's call this map G, then we can take G composed with F. This is going to be a map from W to N. And we can, if you have a differential form at on N, we can take its pullback. Or we can do it, we can first take pullback of eta with respect to F, and then pull back with respect to G. Secondly, this pullback operation is definitely, well, it's additive. So that means this. And lastly, it takes product to product. So eta 1 times eta 2 is F upper star eta 1 times F wedge F upper star eta 2. So in other words, this F upper star is a map from omega star n, and I recall that star means that I take all direct sum of differential forms of all degrees to omega star m, and this is a map of algebras. Map of algebras, where the algebra structure is given by the wedge product. Okay. So let me give you an example. Well, if m is 1, or maybe m is 0, say, then a form, 0 form by definition is just a function. And f star of f is simply the composition of this function. Oh, it must be n. And so I have map f, and this is my capital F. So if I have a function on n, I can take its composition with this capital F and get a function on m. So that's how the pullback behaves when m is 0. So second property is that so we have a very important example of a one form, namely differential of a function. So if you take the pullback of df, this is derivative differential of a function, you get differential of the pullback, right? And using these properties, you can compute pullbacks of any form easily. So so suppose let me give you sort of concrete example. Do a computation. Let's take for f a map from R3 to R2, which is given in coordinates by the formula f of x1, x2, x3 is x1, x2, x1 plus x3. So I use, I call it coordinates here, y1 and y2. coordinates on R2 and coordinates on R3 are going to be x1, x2, and 3. So let's take a compute f upper star of differential form y1 d y1 wedge dy2. So what is written here? So this is the wedge product of differentials of two functions. So that's well defined. And I multiply it by a function. Differential forms form a, so this is, I think of this as a product in my algebra of differential forms of three forms, 0 form and 2, 1 forms. So the pullback respects the product, right? It takes product to product. So I first take the pullback of a function. Well, y1 is, pullback of y1 is x1, x2. Then I take pullback of this one form, and I use this formula here. So this will be d of y1 is, again, this is x1, x2. And then I have d of y2. Y2 is x1 plus x3. And so let's write it in terms of basis in the space of differential forms on R3. So the observation is that this one form, right, that's differential of a function. This is actually differential of product of two functions. And this can be computed differential by the Leibniz form. That's equal to product, say x1 dx2 plus x2 dx1. That's because differential has enjoyed this property. You take the product of this with dx1 plus dx3. And now you do the computation, and so an observation here is that, well, when you sort of develop this wedge product, you get 4 terms, but one of these terms, dx1 wedge dx1, dies, right? Because dx1 wedge dx1 is equal to 0. So in fact, the answer is going to be x1 squared x2 dx 2 wedge dx 3 plus x1 x 2 cube dx1 dx2 and then you have plus x1 x2 squared dx1 wedge dx2 dx3. Okay. So any 2 form on R3 can be written as a combination, uniquely written as combination of these 3 forms, dx2, dx3, dx1, dx2, and dx1, dx3, with whose coefficients are some smooth functions on R. Okay, so so we have, so far we introduced the notion of an algebra on the space of all forms, and we see that there is also every map of smooth manifolds induces a pullback map on differential forms, which is a homomorphism of objects. Very good. Now, whenever you have pullback with respect to smooth maps, or even in particular with respect to diffeomorphisms, you can talk about Lie derivative. Lie derivative of an object, of a form. Okay, so suppose theta is a vector field. So what is a Lie derivative? I recall that a vector field gives a locally defined one parameter group of diffeomorphisms. Phi sub t is corresponding one parameter group of diffeomorphisms. So in the case when M is compact, this is really phi sub t is a globally defined diffeomorphism from M to M, and it has the property that phi sub t plus t prime is equal to the composition of phi of t and phi of t prime. So maybe I'll write it. In the case when M is not compact, it's not globally defined. Instead, what we have is a map from an open subset of M times R. So this is an open subset here that contains M times 0 times 0. And it's map from U to M. So it is understood here that phi sub t of P is defined as phi of P comma T. That's the notation I use. So that means that for every point P, this phi is defined for sufficient in a small neighborhood of point C equals 0, right? So it could be, the picture could be the following. So this is, if this is T, this is sort of M, then this map can be defined on maybe on an open subset bounded by a curve, which is on my picture. So this curve approaches the y-axis t equals 0 when point P on M goes to infinity. So if M is compact, then any such open neighborhood contains a cylinder, and then using this property, we have shown that, in fact, phi is defined on entire M times. So that's what I call by local one parameter group of diffeomorphisms. A map like this satisfies this property whenever both types are defined. Okay? So any vector field theta gives rise to phi. We have shown this. It's basically given by solution to ordinary differential equation. So now so having this phi, one parameter group of diffeomorphisms, we can define Lie derivative of a one form as follows. So I take eta and I take the pullback of eta with respect to phi sub t. So, well, what is this? So for every point P, for a neighborhood of point P on M, this is a family of forms depending on this parameter T, right? It's defined only for small t. And, well, but nevertheless, so it's in a neighborhood of any point. I can think of this as a form that depends on t. And I can take its derivative, right? Forms form a vector space, so I can differentiate this and plug here. Well, the only point where I can take the derivative, right? Remember that it's defined only for small t is when t is 0. That's the only point where the derivative is defined. So it's defined simply as the limit, right? Usual formula. Limit when t approaches 0, phi sub t eta minus phi upper star 0 of eta, but phi upper star 0 is the identity, so minus eta divided by t. Okay? So that's the definition. Let's try to use it. Let's compute something. Okay, so let me check what I have. Yeah, I have some time. Maybe I think I will give an example and then we'll make a break. So the example will be the following. I will take M as R2. And my theta is going to be x d over dy, x d over dx plus y d over dy. And theta, say, is dx wedge dy. And let's try to compute the Lie derivative of eta with respect to this vector. Well, this seems to be a very difficult problem because computing the Lie derivative involves finding this one parameter group of diffeomorphisms, which in turn amounts to finding integral curves for a vector field, which is equivalent to solving ordinary differential equation, and this could be very difficult. So in this case, I can actually do this, and let's see how. Let's try to compute this by definition. So let's find phi sub t. So let's draw a picture of this vector field. So if you have a point, so let's draw a picture. This is a vector field on R2. So let's draw a picture of this vector field. I claim that it's this vector at point. This is the origin at point P is just this tangent vector is just this vector P itself, right? This is my theta of P. So that's the picture of the vector field. Okay, so very good. So this picture should give you an idea of how the integral curves look like. If you imagine that this is a kind of this picture here represents Wien's velocity, then it's clear that if your particle at t equals 0 is here, then it will move along this in radial direction, right? Along this this line passing through your point P and the origin. The only question is, what is the direction? What is the velocity, right? In which velocity, what is the velocity of your particle is going to be? So it's not only the direction that we are interested in, but also the velocity. Well, you see that this vector field is invariant under rotations. So in particular, the phi sub t is also going to be invariant under rotation. So if I can solve this find the integral curve passing through points on x-axis, then I can use the invariance to find the integral curves to all other points, right? Just because this phi sub t is going to commute with rotations because the vector field commutes. So let's look at one-dimensional picture, right? So let's just restrict our vector field to x-axis. Then it will be one-dimensional picture. So theta is x d over dx. It's a vector field on the line. Right? Restriction of that vector field. And let's try to find phi sub t. So it's going to be a one-parameter family of diffeomorphisms of R. So what is the equation for differential equation that we are supposed to solve? We are looking for a function phi of x comma t, which is a map from, in this case, R times R to R that satisfies certain differential equation. And namely, the differential equation is the following, that d over dt of phi x comma t. Yeah, this is the t of x is equal to, so when you at any point x, it must be at any t, it must be equal to the vector field at point phi of x. So it must be equal just to phi of x comma t. So we are solving this differential equation. It's a equation for function in two variables, but we differentiate only with respect to t. So in a sense, it's an ordinary differential equation, but it has kind of extra parameter, it's little x. And the initial condition is that when t is 0, that must be identity. Phi x comma 0 is x. Okay? So we are solving this system of equations. Well, and that's easy to solve. So any solution of this differential equation has the form exponential of t times a function in x. So, and if you want to satisfy this initial condition, you'll find that x comma t is equal to x times e to the t. Okay? So, and now we can write down the formula here. So x y. As I said, it's going to be rotation invariant, so it must be the one parameter group of diffeomorphism is just et x comma y. So this phi sub t is going to be a dilation, right, by this number, e to the t. And it's clear that it takes sum to product. Okay? That's the formula for the one parameter group of diffeomorphism. Now let's use it to compute the Lie derivative. Now the computation is very simple. You just take use definition, so it's going to be d over dt phi upper star t eta, and then you plug t equals 0, and this is I recall that eta is dx dy, so you see that this is d e to the t x dash d e to the t y, and then you take d over dt, plug t equals 0. So here t is regarded as a constant, right? We think of this as a two form in x and y, which depends on parameter t. So this is a constant. You can move it out. So that's going to be d over dt e to the 2t dx dash dy. And now you differentiate this with respect to t. So this is now a constant. And so you get 2 times dx dy. Okay. So this was not easy, right? So we managed to use this symmetry to guess the to compute the one parameter group of diffeomorphism. In general, that's what would be very hard. But fortunately, all we need is to compute. Well, we are not interested in the entire group of one parameter group of diffeomorphism. We are looking only at this derivative. And computing this derivative, as we are going to see shortly after this break, is much easier than you don't need to compute phi sub t to compute the derivative. We will learn how to do this in 20 minutes. Okay, let's make a break. 20 minutes break. Okay, so let's resume. And I'd like to explain for you another way of computing the Lie derivative, which is much shorter. It doesn't involve integration, it involves only differentiation. So, so let's look at some basic properties of Lie derivative. So the properties are the following. Well, so what is the Lie derivative of a function? Remember that a function is an example, is a zero form. So you're supposed to take one parameter group of diffeomorphism and then take the composition of f and phi, and then take the derivative. So essentially by the definition, you get derivative of f along theta. So very good. Now, so one property of derivative. So you have a manifold, you have a vector field, and you can differentiate a function along vector field just by definition. You can identify vector fields with derivations of the algebra of functions. So this is one. Two, what happens if you take the Lie derivative of df? Well, let's compute it by definition. So this is d over dt phi upper star t df, and then we take t equals 0. So the point here is that pullback of differential of a function is differential of the pullback. So this is, well, I will write it as follows. It's d of d over dt phi upper star t f. Then you take t equals 0, and then you take differential of this. So, well, anyway, this is d of L theta f. So you simply differentiate function f on a vector field and then takes differential of that. And the last property that I need is, well, I want to know how the Lie derivative behaves with respect to the product. So, okay. So Lie derivative of eta 1 wedge eta 2. Well, I claim that it satisfies the Leibniz formula. And let's do it again by definition. So we have d over dt of the product phi upper star t eta 1 wedge phi upper star t eta 2. And then we're supposed to evaluate it at t equals 0. So, well, this is a wedge product of differential forms. So, if you choose local coordinates, every differential form can be written as a combination of some of basic forms, dx1, dx2, dx3, and so on. So you can think of this as of this form as right here, as sum of h pt dx at I1, wedge, and so on. So you can think of, so the coefficients depends on t. When you take the wedge product, well, you basically take product of the coefficients, right? And plus this product, the coefficients of the product are linear combinations of the products of the coefficients. So you can apply the Leibniz form to compute the derivative. So this is equal to, well, you first differentiate this term and multiply it by the value of the second form when t is 0. When t is 0, this is eta 2. So what you'll get is Lie derivative. I will write down the answer of theta 1, which eta 2, right? So plus eta 1, which Lie derivative of eta 2. This formula is an immediate corollary of the usual Leibniz formula for the functions in one variable. Okay, so we have these three basic properties, and let's see how we can use it. Let's go back to the example we have already done. So we take for M_R2, vector field theta will be x d over dx plus y d over dy, and eta is dx dy. So okay, let's do the computation. So first we differentiate x with respect to this vector field, and what you'll get is x. So I will write it as follows. It's d of L theta of x, right? Wedge dy plus dx wedge d of L theta y. This is the Leibniz formula. Now, if you differentiate this vector field, this function x along this vector field, you get x. So this is dx wedge dy plus dx wedge dy. Okay, so this is much easier. Very good. Now that's all. Now about Lie derivatives. So let's the next operation, very important operation with differential forms, is the Duran differential. Okay. Differential. So, what is a Duran differential? I will first explain for you some properties. This is a map from differential forms of degree m to differential forms of degree m plus 1. So what you have to remember about this map are the following properties. Well, property one is that when m is 0, d takes f to its differential. Right? So we already know what df is. Property 2 is that if you take the composition, if you take any differential form and apply d twice, you get 0 for any eta. And property 3 is that so D satisfies the Leibniz formula. So the Leibniz formula takes the following form here. So alpha and beta are going to be forms. And so the differential of the product, well, it cannot be product of differentials, right? Duran differential increases the degree by 1. So it must be, so if, say, this is alpha is in omega n, and beta is another form. So this guy must have degree m plus L plus 1. So what I can do, I can take d of alpha and multiply it by beta. And then, so I want to write down the Leibniz formula, except that it's going to be a graded Leibniz formula. So dB, where the sign here is -1 to m. So it depends on the degree of alpha, not of degree of beta. So so that's how it works. And the fourth property here is the following: that if you have any map, smooth map from M to N, then the Duran differential commutes with pullbacks. So Duran differential of F upper star eta is equal to F upper star D eta. So, and theorem here is that there exists a unique D with the above properties. So, well, properties. So that means that, first of all, well, D exists, so I need to comment about the uniqueness. I'm not saying, so property 1, 2, and 3 refer to the Duran differential on differential forms for a fixed manifold n, whereas property 4 has to do with all manifolds, right? And morphism between manifolds. So I'm saying that there exists kind of a unique way to construct this D for all manifolds simultaneously. So I really need to use 1, 2, 3, and 4, right? In this sense, D is unique. And this is easy theorem, but it's extremely important. So before I give a proof, let me give you an example how you use property 1, 2, and 3, and 4 to compute the Duran differential. It's easy. So let's let's just take R2. and M is R. So Duran differential of a function, well, it's differential of a function, so it's equal to df dx plus partial derivative with respect to y times dy. Now suppose I have I can apply the Duran differential to 0 forms and to 1 form. The Duran differential of 2 form must be 0 because there are no 3 forms. So the Duran differential of 1 form, say g dx plus h dy. Well, first of all, it's yeah, I have to say this is linear, or maybe I didn't say it. This is a linear map. So it takes sum to sum. D of alpha plus beta is equal to d of alpha plus d of beta. That's kind of property 0. Okay. So now this is d of g dy plus d of h dx dy. And now this is what's written here is a product of 2 forms, so I can apply the Leibniz formula. And how does it work? It gives me dg wedge dx plus g g wedge, well, don't write wedge here, d of dy and then I have dh so this is 0 form, so I have no sign here. Also, sorry. This must be x. Then I have dh wedge dy plus another term h d dy. Okay, so d squared is 0, so these 2 terms go away. So what is left is sum of these 2 terms. So now let's plug here for dg this expression for part A, from part A, and use the fact that dx wedge dx is 0. Then what we'll get is negative dg over dy dx wedge dy. So why do we get negative sign here? Because dg is sum of this partial derivative with respect to x times dx, but this term goes away, right? Times this partial derivative, but so you'll have partial derivative of g with respect to y times dy times dx. And I interchange these 2 factors and get negative sign here, plus d h dx dx dy. And this gives me the formula. This is equal to d h dx minus dg dy multiplied by dx dy. So that's how you compute the exterior derivative, the Duran differential of a form. And so let's compare these two formulas. So D, the theorem asserts that there exists a unique map D that satisfies all these four properties. And in particular, we must have the D of the Duran differential of df must be 0, right? And df is just combination of partial derivatives. So that's going to be the assertion that d squared f dx dy is equal to d squared f dy dx. So if you take the partial derivatives in two different orders, you get the same function. This is a well-known property of two-dimensional calculus, and this property is equivalent to the equation that d squared is 0. Okay, very good. So at least it's this computation suggests how you define the Duran differential for R2 and why it works, why d squared is 0. Very good. Now, let's give a proof of the theorem. Proof is very simple. You prove it for Rn. So let's suppose you have an open subset of Rn. Then there exists a unique map D from differential forms on U to differential forms. So M ranks from 0 to infinity. Satisfy property 0, linearity, 2, 1, 2, and 3. All right? So 0 means that d takes sum to sum. 1 means that Duran differential of a function is its derivative. 2 means the Leibniz formula, and 2 is the fact that d squared is 0, and 3 is the Leibniz formula. The proof is, well, so first of all, uniqueness. So any form on Rn can be written as combination, linear combination of forms of the following type: a function times dxi1 wedge dxi. So in order to prove uniqueness, I just need to show that there is only one. Well, suppose I have two maps like this, D and D prime, satisfying all these properties. It's enough to show that D is equal to D prime on forms of this type. So let's use property 0, 1, 2, and 3 to compute D of this. Suppose that it exists. I want to show that its value is determined by 1, 2, and 3. Well, this is product of a function and forms, and D. So you can apply the Leibniz formula many times, right? That's so we have Leibniz formula for the product of two forms, and by induction we get a Leibniz formula for product of any number of forms. And when you apply D to D of something, you get 0 by property 2. So that must be equal, by the Leibniz formula, it must be equal to df wedge dx1 I1 wedge dx I m, right? Again, so this follows from the Leibniz formula. And the fact that D composed with these. So that's the end of the proof of uniqueness, right? So if D exists, it must satisfy this identity. So existence I will not give you a complete proof. Define D by this formula, and then one has to check that D squared is 0. That's the only thing that you, well, so just use this formula. This is a basis. So at the end, any form can be written as a uniquely represented as a linear combination of forms of this type. So this formula gives a well-defined operator from omega m to omega m plus 1. The only thing that you have to check is that property 1, 2, and 3 hold. I will not do this. Well, 1 holds by definition, so you need to verify property 2 and 3. And so property 2, for example, asserts that D squared is 0. It turns out that, and it is easy, that 2 is a formal corollary of the fact that of the fact that we already used in dimension 2, that the two partial derivatives, that if you have a function in two variables, then differentiating it with respect to x and then with respect to y is the same as differentiating it in the opposite direction, order. So this is kind of was the key to the this identity. D squared is 0 in two-dimensional case, but it turns out that the same property implies 2 in general. And 3 is property C. The Leibniz formula is straightforward. Okay, so so we have modular the easy computation that I have omitted. We have the uniqueness of existence for open subsets of R. But now we can prove. We can do it. We can prove the theorem in general, and it's not hard. so maybe one corollary of what we already proved. So suppose I have two open subsets U and W in array. And suppose I have a diffeomorphism. So if I have a form eta on W and take its pullback and get a form on U, right? So now I have by the lemma, I have the Duran differential of eta, and I also have the Duran differential of phi upper star of eta. So a priori, this depends on the embedding of U in Rn. It defined in terms of coordinates, right? So U is an open subset of Rn, so we can apply the lemma and get a, well, that's going to be a form m+1 form on U, and this is m+1 form on W. So I claim that the following property holds. Okay, why that? Proof. Both sides satisfy the Leibniz formula. What does it mean? It means that if you replace eta by the product eta 1 times eta 2, then you'll have the so for example, phi upper star d eta 1 wedge eta 2 is going to be f upper star d eta 1 wedge eta 2 plus and here I need to put phi upper star, and then plus phi upper star eta 1 wedge d upper star eta 2, and here the sign is -1 to the degree of eta 1. So you have this formula that expresses this operator applied to the product to sort of the operator applied to factors. And the same formula, and similarly here you have, you can apply the Leibniz formula here, and you get a similar expression. And therefore, it's enough to, in order to verify it for all forms, it's enough to verify it for just for generators, for functions, and for derivative of a differential of a function. But for functions, you get it sort of for free. It's just the fact that taking differential of a function commutes with pullback. We already discussed it. And for the differential of the function, you know that d squared is 0, so you get the result. Well, another way of putting the same kind of phrasing the same proof would be the following. This property is equivalent to saying that d eta is equal to phi inverse upper star of d phi inverse eta. And now we could use directly the uniqueness part of the lemma, yeah, right? Uniqueness, to verify that the left-hand side and the right-hand side enjoy property 0, 1, 2, and 3. So for the left-hand side, we know this by construction, and all you need to verify is that you have it here, which is straightforward. Okay, so now having this this corollary, we can give a global construction of the Duran differential. So here is what you do. Existence. No, maybe let's first start with uniqueness. Uniqueness of D. Okay, so take manifold M and take an open chart. Well, suppose you have a form eta. So in order to prove uniqueness, I'll just write for you a formula, which is a corollary of the axioms, which must be satisfied, that characterizes D of eta uniquely. So, well, this must be m+1 form on M, and it's determined by its restriction to open to charts. So let's describe this. So, okay, I have this diffeomorphism, so I can write this restriction is, well, first of all, the Duran differential must commute with the restriction, because restriction is a special case of the pullback, right? It's pullback to the open subset. So it must be D of eta restricted to U. So this must be differential. Now I take eta restricted to U. U is diffeomorphic to W. So my differential form on U is the pullback of a certain differential form on W via this map F. Namely, this is F inverse star of eta restricted to U. And then I take F upper star. Right? So this is a form on W, and I take its pullback, and I get back my formula. So, and this is equal to D F upper star. So the Duran differential must commute with F of F inverse eta restricted to U. And this is already formed on W, and W is a subset, open subset of R. And we already know that properties 1, 2, and 3 determine uniquely the Duran differential in the case of open subsets of R. So we know this expression, and therefore we know everything. So this proves the uniqueness. Okay? So let's use this, let's give a name to this formula. So I claim that the existence well, follows, can be shown as follows. So define D locally by this formula. So what does it mean that you define it locally? You pick an open chart, and then you define the restriction of d eta to u. We have the formula. And all you need to show is that these guys glue. So it means that if you have two open charts, then these forms agree on the intersection. But this is immediate. So what does it mean that you have two charts? You have and use corollary. So it means that you have some open subset and two maps, two diffeomorphisms between this open subset and open subset in open subsets in R. This sits inside that. But then you have this diffeomorphism, and the fact that the two forms agree, so that this expression does not depend on the choice of diffeomorphism between U and W, is equivalent to the formula here, to this formula. Okay? Applied to the diffeomorphism between W and W prime, which is composition of this one and the inverse to this one. Okay? So very good. So we have various operations. Let's let me proceed with another operation, vector fields that you, or maybe, sorry, before I explain what a substitution of a vector field is, let me give you one application of the Duran differential. So the Duran homology. This is something very interesting. So, so we have, suppose you have a manifold M, we have zero forms, functions. We have one forms, we have two forms, and so on. And we have maps given by the Duran differential. And these maps so these groups together with this homomorphism form what's called a complex. So D composed with D is 0. In other words, if you consider the kernel of the map from omega m to omega m plus 1, the kernel of the Duran differential, then it contains the image of the Duran differential from omega m minus 1 to omega m. So in particular, I can take the quotient of one group by the other, right? So if my element, if I have a form which is in the image, it means that it's D of something, and it means that it's skewed by D, because D times D is 0. So I want to take the quotient of one enormous group by another enormous group. That's what you do when you have a complex. You can take its homology. It's defined by this to be the quotient of the kernel of this map D by the image of the previous one. And in this particular case, when I have the differential forms, it's called the Duran homology, nth Duran homology of N. So this space is called the space of closed forms. Closed forms. So a differential form is said to be closed if D of it, its Duran differential is 0. And these are called exact forms. So if I give you if I give you say a one form on R2, then so you may ask whether this one form is differential of a function, right? So let me rewrite this a little bit. Okay. Let's look at some examples. So let's take for my manifold M just R. Well, so H0 Duran of M, this so this is just the kernel of this map by definition. I declare omega -1 of M to be 0. This is kernel of map from functions to one forms. So I'm looking at function whose differential is 0. That means that it's all locally, it means that it's all partial derivatives at 0. So these are locally constant functions. Functions on M. So in particular, if M is connected, then it's always if M is connected, then any such function is actually constant. So let's look at H1 Duran. R. Well, any form, one form on R is closed because there are no two forms. So this is just the co-kernel of the map from functions to one forms. And well, this map takes function f to f prime dx. And it's well known that this map is surjective because for any function there exists primitive. So the co-kernel is 0. So in the case of my manifold is R, you have the Duran homology in degree 0 is just R, the Duran homology in degree 1 is 0. Let's consider case when M is R2. Okay, so what happens here? So H0 is R because M is connected. H1 is already interesting. So so you have you look at one forms. You can write one form as f dx plus g dy. And you look at closed one forms, which means that the Duran differential of this is 0. And this means that dg over dx is equal to df over dy. So eta d eta is 0 if and only if you have this property. And question is if their h is smooth function on R2 such that f is dh over dx and g is dh over dy. So in other words, we are given two functions f and g, and we want to solve this partial differential equation. That's equation for function in two variables. So partial derivatives are given. So this condition gives a necessary, this is a necessary condition for such h to exist, right? Because, well, the two second order partial derivatives must be equal, right? So if h exists, then we must have this property. That's equivalent to saying that any exact differential form must be closed. So the real question is whether, given f and g satisfying this property, we can find h like this. This is not. This is not. You can. I don't want to. So we will start next lecture by proving this, that h1 of R2 is in fact 0, by proving that for any f and g with this property you can find h. So this requires a little bit general. Well, we'll prove much more general assertion than this. We will prove, for example, that the Duran homology of any manifold M multiplied by R by a real line is the same as the Duran homology of M itself. So in fact, the Duran homology of M times R is Duran homology of M. In particular, H1 of R2 is the same as H1 of R. But well, you can, as a very good exercise, you can try to find the direct argument for R2 and 1/4. Just construct H explicitly using some integration, kind of integration. The idea is very simple. You define function H as integral. You first integrate sort of this form. You integrate this form along half of the rectangle. This is origin, and you define H to be integral of f dx plus g dy over this space gamma. And this is H of x comma y, right? This is gamma. So, well, there is something to prove here. So you need to verify that partial derivative of H with respect to x and y indeed satisfy this property here. And though it is easier for one partial derivative, namely for derivative with respect to x, it's not easy for the second derivative with respect to y. And here the idea is that you must use that this integral along this space is also equal to the integral along this space. Gamma prime. You can integrate also this form along another path, gamma prime. So the fact that the two integrals are equal is a corollary of a classical theorem in vector calculus known as Green's theorem, or which is a special case of Stokes' theorem. So you can express the difference of the two integrals as the integral over the interior of this rectangle of something, and this something happens to be zero, provided that this condition is satisfied. So I will leave for you to kind of complete this line of argument and show that H1 of R2 is zero. In fact, H2 of R2 is also zero. So in general, for Rn, H0 is going to be R, and all higher homology groups vanish. So here is another example. So see, let's take for M S1. Again, H0 is R. That's not very interesting. And let's just compute H1. So we have a very explicit description of 1/4 on S1. This is F times d theta. And any one form is closed because there are no two forms. So in functions, just this is 1/4 on the circle. And this is, I also have functions in the circle. There is this map D, which takes F to df. And the question is whether this map is surjective or not. So, well, I claim that the answer is not. And so it's not surjective. And in fact, the Duran homology is going to be isomorphic to R. So in order to show this, I will construct a map from one forms on S1 to real numbers. And I will give you a formula for this map. This map is called the integral. And so it takes this one form to integral of function f, well, dx from 0 to 2 pi. Okay, write it like this. So what is written here? So so this is my circle, and I have a function f on the circle, and I can think of this as a 2 pi periodic function on the real line. And I put coordinate theta on this real line, so I integrate my function, periodic function, from 0 to 2 pi. So that's well defined, and it's a number. So now I claim that so if my form is differential of a function, then this integral is going to be 0. So integral of df, this is notation for the map from omega 1 S1 to real numbers. I take a form and send it to this integral over the interval. So I claim that this integral is equal to 0. Okay, indeed, it's equal to, by the Leibniz formula, so this is integral from 0 to 2 pi of f prime d theta. And that's equal to f of 2 pi minus f of 0. But f is periodic, so this is 0. So that means that this map, integral over S1, defines a homomorphism from the quotient, from the co-kernel of D. So get a map from the Duran homology of S1 to real numbers that takes omega to integral over S1 of eta. So this is well defined, again, because the map is 0 on the image of the differential. For example, and it's clearly surjective. For example, integral of d theta over S1. Well, it's easy to compute. It's easy to compute because, well, this integral is equal to, you can take a very small number epsilon and integrate from 0 to 2 pi minus epsilon. But, well, well, this integral is easy to compute because theta is, though it's not a single valued function in S1, it's a single valued function on the interval from 0 to 2 pi. So it's, by the Leibniz formula, it's just equal to 2 pi. So this map is clearly surjective. right? It takes one form at least to 2π. It's non-zero. It's a real vector spaces. And I claim that, in fact, this map is an isomorphism. So in order to do this, you have to show that if the integral is 0, then your eta is differential of a function. And this is also not sorry. This is also not difficult because, well, what do we have? We have a one form eta on the circle, and we want to construct a function on the circle whose differential is z. And the function on the circle is the same as periodic function on the real line. So let's try to construct a different function on the real line. So we have what I want to have is we have functions on the real line. Any function on the circle can be considered as a periodic function on the real line. And we also have one forms on the real line. And any one form on the circle can be viewed as a differential form on the real line, just because the real line maps to the circle, right? The circle can be identified with the quotient of the group of real numbers by integral multiples of 2π. So the pullback map gives you this inclusion. So this is the Duran differential. Here it's surjective. We already know that for real line it's surjective. So take a one form, view it as a one form on R. So that means that you simply you write it as f times d theta. Theta is now a function on R. And then you can essentially uniquely up to a constant, write it as a differential of a function. So you take primitive of this f. And so the question is whether this primitive of f is a periodic function. So to summarize, we have an arbitrary periodic function and we take its primitive. The question is whether the primitive is again periodic. And the answer is that in general, no. And a necessary and sufficient condition for the primitive to be periodic is this, that this integral is 0. Let's complete the proof. So, well, all these three examples, computation of the Duran homology, well, that is, I strongly recommend to to look carefully to look through all the details in the argument that we briefly discussed, because these are very instructive examples, and many ideas that we are going to discuss later on are generalizations of the kind of basic principles that we used already. We have seen here. So Neuron homology is something that relates kind of on the one hand, it's determined by, it's defined using differential forms, some kind of complicated objects which infinite dimensional vector spaces, motion of one infinite dimensional vector space by another infinite dimensional vector space. On the other hand, a deep theorem, well, rather a deep theorem in differential geometry or differential topology is that the Duran homology of any manifold M is a finite dimensional vector space of real numbers. Moreover, it's in fact, in contrast with a very complicated definition, again, it's a quotient of two infinite dimensional vector spaces, it turns out that the Duran homology is rather easy, is computable. So for we'll see how you can compute the Duran homology using, for example, a triangulation of your manifold. Okay, so that's with this I want to. That's all I have for today. So I send you a list of seminar problems, and we will discuss these problems next time. And I also promised to you some homework problems, well, computation mostly. And I'm sorry for being late. I haven't yet done this, but I will send you the problems tomorrow, and it will be due in 2 weeks. Thank you very much. Any questions?
So the question: why we didn't define Duran homology? Is it well defined?
I don't understand. So the definition of the Duran homology is given here.
Homology. But not...
Homology. Well, and can you suggest a definition?
Is it not functorial in some sense? Is it not well defined? I have not seen this definition.
Well, so in algebraic topology, indeed, one has first introduced indeed singular homology and then singular cohomology. And in some sense, singular homology is a more fundamental object. However, if you look at homology with rational or real or complex coefficients, and then it is well known that homology of a topological space, say with real coefficients, is simply dual to singular homology of the same topological space. So in this sense, well, both groups are functorial. One is contravariant. It means that so if you have a map from X to Y, you have a map on the homology groups in the inverse direction, from homology of Y to homology of X. And on homology, the map goes in the different direction, so it's a covariant function. But if so there is a kind of easy way, there is a simple relation between these two groups. And well, if you, for example, know that if you consider spaces for which homology is finite dimensional, and this is the case for manifolds, then then homology is simply dual to homology. Twice dual is the identity functor on finite dimensional vector spaces. So So in this sense, homology, the difference between homology and cohomology is not that big. However, in the RAM theory, one can talk about differential forms or Duran homology classes, so closed forms, modulo exacts, and one can also talk about integration of differential forms, closed differential forms, along closed submanifolds. So, for example, imagine that you have a torus, two-dimensional torus. So it's a quotient of R2 modulo lattice. You can look at closed one forms on the torus, and we will show that there is a well-defined operation that assigns integration. You can integrate a closed one form along any closed path. In fact, you can integrate any form along any path. But for closed forms, the integral along a closed path is deformation invariant. So it means that it depends only on it doesn't change if you deform this path slightly. And this integration underlies one of the key results in theory in kind of differential geometry, the Duran theorem, which gives you a pairing between singular homology and Duran homology. So, so this thing, what I'm saying is that singular homology comes into the game in a very essential, beautiful way, which is not similar. So in algebraic topology, again, the difference between homology and homology is not that big. In the RAM theory, it has a form of pairing between cycles, like closed submanifolds, and closed forms. This pairing is given by the integration, and it's kind of, it's deeper. The relation now is deeper than in singular homology and homology theory, where just sort of this formula holds tautologically. Okay, does it answer your question?
You mean that the role of Duran homology plays singular homology?
Well, so
by theorem.
One way to formulate Duran theorem is that for any smooth manifold, a singular homology of this manifold is isomorphic to the Duran homology. But so saying that two spaces are isomorphic is not a meaningful statement, right? It's just the quality of dimension. So the pairing, right? The isomorphism is given by the pairing between singular chains and differential forms given by the integration.
Okay.
Okay. Right. More questions? Okay, if not, let's stop here.
Poincare pairing, yes?
Yes, that's Poincare pairing, right. So what we have here is an example of the Poincare pairing. You see it's given by integration of forms by closed path by S1. In this case, we only have the singular homology group is also one-dimensional, and the isomorphism, the Duran theorem is precisely the assertion that this map given by the integral is an isomorphism. So in the case of S1, we have already proven the Duran theorem.
We have proven that this pairing is non-degenerate.
Yeah, it's non-degenerate.
Okay.
Very good. Thank you.
Thank you.
See you.